Okay, for any online or absent people, here's my explanation of energy and what it is. Energy is the money of physics, right? So if I give you some money, I lost the money and you gained exactly that much money. It doesn't disappear, it doesn't change, it transfers from account to account, but it's never created or destroyed. Okay, it's constant over time. Actually, real money doesn't quite work that way. The value of money keeps changing ever so slightly. But that's the purpose of it, right? Who decides if I try to sell you my lunch because you're tired of the school lunch? Who decides how much my lunch is worth? I do. What if I can't sell it? Then it's what it's worth, whatever someone will pay for it. So, and likewise with energy. What is the use of energy in physics? It really is. It's made up, just like money. Who says those little paper bills? It's all the same paper. It's got different stuff printed on it. So by the different configuration of ink on a 20 or 100 or $5 bill, it's worth that much different? No. It's exactly the same. You decide that it's worth that much. And you decide, I'm going to trade this Franklin for 20 Lincolns, and so on. Okay. What energy is this just what money is. It's keeping track of all the physics stuff, except for one thing. Can you guess what one thing we don't want to keep track of? Pounds? Oh, not. Though we have newtons, we are keeping track of them. What was it that didn't change? Oh, good. We do get to drop direction. That's just convenience, though. If energy, so we made up energy, just like we made up money. Energy is never created or destroyed. That means it's constant in what? Oh dear. If it's never created or destroyed, then it doesn't change over time. Okay. We're not going to keep track of the time. It doesn't matter when I traded my lunch for $100. I got the $100 now, and you're about to realize I don't eat lunch. So you got nothing. Remember back when we had some silly equations, we call them 1 and 2, and we solved them, and we got rid of time. There's that 1/2 there. We canceled out the time once upon a time, weeks ago. And what did we get? We call it equation 3. And it goes like this. Okay, final velocity squared equals initial velocity squared plus 2 times acceleration times the displacement. Okay, I'm going to start scrolling down, so hopefully have that top part in black. Okay, well, now we know a lot more about acceleration. We know you have to have a net force, and only a net force causes something to accelerate. If you don't have that, you don't have acceleration. You get zero acceleration. Things stay the same, or at least at constant velocity. Okay? Now I've seen math teachers at Westside do this. I know it's a legal move. I used to think only physicists did this. I'm going to distribute the quantity m mass divided by 2 over this whole equation. Okay, distribute it all. I'm not going to draw my lines everywhere. And I also want to move this initial velocity squared term to the other side. So I have 1/2 mv squared minus 1/2 mv0 squared equals mass times acceleration times the displacement, which is net force times displacement. Oh man. So I have just mass and velocity on one side. And I'm going to say, whoops, we don't abbreviate like this in AP Physics. This 1/2 mv0 squared is the kinetic energy, the energy it has because it's moving, because it's a thing with mass, and it's moving, and that's all there is on that one side. That's why it's called kinetic. Kinetic energy, 1/2 mv squared. It's kind of like the mv squared over r, and it's mv squared over 2. We don't need r. We'll get to energy in a circle later. That's a couple chapters down the road. We'll combine them. Then you'll really start to pull your hair out. But for now, it's fine. Linear velocity, same old from chapter 2, v. Okay. I don't think, yeah, that's right. It's a pain in the butt to do, if you have Vx and Vy, you have to do Vx squared plus Vy squared, you separate categories. And so that makes it too much of a mess. Okay, so we won't even do 2 dimensions. We're just going to call this right side the work. Okay, the net force times the displacement that actually happens. Okay, so we're going to focus mostly on that one, because that's where there's difficult stuff. But this is actually, AP Physics has to know, this is called work-energy theorem. The change, that's why I wrote that with a minus like that, the change in kinetic energy equals the work done by the net force. And it's a little bit complicated because you can break apart, the net force has different pieces inside it usually. And so different forces are doing different amounts of work depending on how much displacement you actually get. Sure. Oh, yes. So, I think it was up there at the top. Oh no, it's coming up. Hopefully you notice that if you take kilograms times meters squared over second squared, you get the same thing as if you take newtons times meters, right? Because newtons was already kilograms times meters per second squared. We call this a joule. I had a Texan professor who said joules. But we need a new unit. I'll tell some fun stories about it later. Okay, but I don't want to get too sidetracked. Instead of writing kilograms times meters squared over second squared, blah, look how many symbols that is. 1, 2, 3, 4, 5, 6, 7 if you include the line. 8 with the dot. No, let's just do capital J because it's getting ridiculous. So it's really just convenience. It's joules of energy. You might never have heard of joules, but you've heard of its cousin, the watt. A joule per second. That's coming up later this week. 1 joule per 1 second is a watt, like a kilowatt hour that your house is powered in, that your, that's right, your phone charger can provide so many watts of power. Okay, so we're getting back to almost some familiar units. Excellent. Okay. There's a really important rule. Okay. Only the net force and the actual displacement do work. So if you have displacement 0, no total work got done. If you have displacement in the x direction only, no work got done in the y direction. Okay. Only the true net force and actual displacement count. Okay. Come on. I should mention this now. I think I forgot in the other class. So if you have a force, that's why we actually, the dot product has a special meaning here. Okay. when we do this product, when we multiply force times displacement to get the energy or the work done, we include only components of F that are parallel to the displacement. Okay? And put in parentheses, that involves the cosine of the angle between them. Okay? What that effectively means is we get to, we'll just redefine our axis. Whatever direction it's happening, only the displacement direction matters. So we'll change or we'll rotate our axis around, just like on the incline, so that the direction that the displacement actually goes in is positive x. And then we'll measure any angles from that axis. Okay? It basically comes out just like you've done before. How am I on time? Okay. I need to pause pretty soon and cut my video. Any questions so far? Okay. Let me pause that and I'll click over to video. Okay.